Today we're going to take a look at section 1.2, and we have talked a little bit about patterns in section 1.1, but we're going to explore this idea a little bit more thoroughly in 1.2. The whole section is about exploring patterns. So the first thing I'd like for us to take a look at is a little bit of vocabulary so that we can talk about things and make sense when you're reading questions in as much as anything else. The word conjecture is a statement or a conclusion that has not been proven. So sometimes something will say, make a conjecture about what's going on. So for what you're working on, it's not going to be something usually that you can prove is true, but you're looking at it and you're making an educated guess using the information you're given about what you think is happening. That's all a conjecture is. There are two types of reasoning. There's inductive reasoning and there's deductive reasoning. Inductive reasoning is making a generalization based on observations or patterns. This is what happens when I wake up in the morning and I tell my children, well, the last few days have been cold, so it's probably going to be cold today. Right? I'm making a generalization about what's happening next based on what's been happening already before. Or it's going to be cold for the next week because it's been cold for the last week, that kind of thing. And in Oklahoma, of course, that doesn't work very well. All right, so deductive reasoning is the use of mathematical axioms, theorems, definitions, undefined terms, assumed to be true for logic or proof. So you're using something that you know is for sure true and accurate to make the decision about what's happening next. Okay, it's a more sure way of predicting. And when we get to some examples of this, I'll show you the difference between the two. It looks a little bit different right now, but I'll show you. And then the last thing here is a counterexample. A counterexample is just an example that shows something to be false. Okay? So all it takes for me to say all the stuff about the weather is that tomorrow we end up having something where it's a freak snow day, right? So that would be a counterexample to what I intuitively thought was going to happen. Just something that proves something to be false. All right. Sequences are simply an ordered arrangement of numbers, figures, or objects. We're going to work with numbers, but patterns don't just include numbers. I remember some pattern books that my daughter had when she was in kindergarten. My son has brought home some of the same kind of thing where it's red triangle, blue square, green circle, red triangle, blue square, what comes next? That's pattern, right? The kids have to recognize the shape, or they have to recognize the color, or the number of things in a certain way. Those are patterns. Those patterns are called sequences. An arithmetic sequence is specifically designed around the idea of the number, though, having a pattern where we've got a sequence of numbers in a row. This arithmetic sequence is one where each term comes from the term before by the addition or subtraction of a fixed number. So we've seen some of these. You saw them in your previous homework where you had this sequence. And you know them as the even numbers. I mean, I recognize that. But they're also an arithmetic sequence. I can predict the number that comes next by simply adding what to the number I have? 2. And I can keep going in this sequence based on that idea. Okay? What I'm doing right now is inductive reasoning. I'm making a prediction about what's happening next based on what's previously happened. That's inductive reasoning. That number that you add, in this case 2, that Brenna said, is the common difference. It's the number that gets added to get the next successive term. And it could be subtracted, right? So I could have had the numbers that looked like this. So let's say I had this set of numbers. I know I don't have very many of them up there, but what number would I subtract to get the next number? It's 3, so we would call negative 3 the common difference. We'd use the number negative. Okay? So we'll say the sign that's associated with it when we talk about the difference. All right. A recursive formula is a formula based on the pattern established after one or more consecutive terms are given. It's a rule that shows how to obtain each successive term based on the term before. That's what you're doing when you're saying, I added 2. You're saying, start here, add 2. That's a recursive formula. But that will only work if you know where you're starting from, right? If I tell you my sequence is add 2, you still don't know what my sequence is because you don't know if I'm talking about the even numbers or the odd numbers. You don't know if I started at 5 or at 52. So your sequence is determined based on at least one of the numbers in the sequence and the pattern or the recursive formula for how you get the rest of them. That's one way to do a formula. The second way to do the formula is to use an nth term. This is a formula used to find the term in the sequence, and you don't need to know any prior terms to do it. Okay, we're going to create nth term formulas. That's how we're going to create our formulas when we move on to the next slides. Okay, so that we won't need to know where we start in the sequence to actually get the whole sequence out of that. All right, I want to show you this example for Fibonacci. A Fibonacci sequence, this is the Fibonacci sequence, and it's a little different. Has anybody seen a Fibonacci sequence before? Is that something familiar? A couple of you have. Fibonacci sequences occur in nature. I can say it that way, say real life, but they occur in nature. And so when you see different objects, you'll see sometimes posters in teachers' classrooms about Fibonacci sequences. And so you see the shells that go around, right, and they get larger. You guys know what I'm talking about, like the snail shells. You'll see sometimes rings on a tree. They grow in a Fibonacci pattern. And a Fibonacci pattern, notice, is not this arithmetic business that we're talking about. I can't go from 1 to 1 to 2 to 3 to 5 and add the same number every time to get the next one. Can I? But there is a way to get to the next value. So I'll put you girls on the spot. If you don't know the answer, that's fine. Do you remember how to do it?
You add the two numbers together, like 1 plus 1 equals 2. You add the previous sequence.
Good. And it's the previous two numbers, just like what Taylor said. So if you add the two numbers prior to the number together, you get the next number in the sequence. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And so on. Does everybody see that? So in order to do the Fibonacci sequence, it's actually only defined in terms of this recursive idea. We have to actually have the sequence to create the rest of the portions of the sequence. So if I wanted to know the next number in this sequence, what would the next number be after 21?
21.
And that would give me what? 34. Could we go on? Okay, what would be next? 55. And so on, right? We just add the previous two numbers together to get the next number in the sequence. So a Fibonacci sequence is already a sequence that's set up as a recursive pattern. There's one other type of sequence that we'll talk about, and that's called a geometric sequence. There's a relationship to geometry. We're not going to talk about it from that perspective, but that is where the number is coming from. A geometric sequence is one in which each successive term is found by multiplying or dividing by a given term. So in a geometric sequence, we're able to multiply or divide by a number to get the next number in the sequence. That number that we multiply or divide by, that's called the common ratio. And that number doesn't have to be a whole number, although it will be on many of the ones we're looking at. So maybe we multiply by 2. So maybe our sequence looks something like this. 2, 4, 8, 16, and so forth. Right? We could do that. In that case, we would be multiplying by the number 2 every time. But we could multiply by the number 2/3. That's why we see the word ratio used in this for common ratio. And then this leads us into the need of defining something, and it's defining what powers look like. So if we have a to a power of n, what we mean by that is that we have a multiplied by itself n times. Not added to itself. We did the add it to itself when we did Gauss's method, right? Where we said, oh, we're going to add the number 101, 15 times or whatever. We did that one. This is multiplication. So if we multiply a number by itself n times, that's a power of that number. And you guys know that if you had 4 times 4 times 4 times 4 times 4, that's the same as saying 4 to the 5th, right? Okay, so these are exponent powers, and that works for any time n is a natural number. Again, and natural numbers are the counting numbers. When you first learn to count, you start with the number 1 and you go up from there. So we need to define for what we're working with what happens at n equals to 0. So when n equals to 0, and the 0 is the exponent, a raised to the power of 0 is 1. And I'm not going to describe why, because we're going to get into that when we get into chapter 3. But for now, it's just a rule. Absolutely hate saying that like that way, but we're going to do it later, I promise. Okay, so for now, a to the 0 is just 1. All right, so we're going to do some now. We have 4 numbers, and we're told to list the next 3 that are going to occur. We're going to identify if the sequence is arithmetic or geometric. And we're going to do one more thing that's not written in here because you're going to be asked to do it at some points, is we're going to find the nth term, or sometimes it'll be called the nth formula, the nth number formula, or the general formula, the general term. Any of those mean the same thing. It's going to have something where it's got an n in it. All right, so that's going to be the last thing we do when we look at this. So the first one we're going to do, it says we have 1, 4, 7, 10. Is it arithmetic or geometric? It's arithmetic. And why is it arithmetic? It's arithmetic because we're adding 3. Okay, so that's the first piece. Is everybody good with that? Everybody sees why that's the case. All right, so we're going to figure out then what in the world we do in order to get a formula for this. Now, I can find the next 3 terms without a formula, so let's just do that real quick. What comes after 10? 13, 16, 19. But let's say somebody wanted me to find the 50th term in this sequence. I do not want to keep adding 3 until I get to the 50th value. That seems sort of like there's got to be an easier way to make that happen. And there is. So here's how we do this. This number that we add, do you remember what we called it? Common difference. Very good. This is the common difference. You take the common difference, in this case it's 3, and you multiply it by n. That's how you increase by 3 every time. However, if you notice, if I were to put in n equal to 1 here, what would I get? I would get 3 times 1, which is 3. And n equal to 1 should be the first term in my sequence. So somehow I've got to fix the fact that my first term is supposed to be a 1, but if I put the number 1 into this equation that I'm creating, it didn't work. Well, the way we fix that is we simply add or subtract the value that we need to make it work. So this is minus 2. Why is it minus 2? Because if I put in the number n as 1, sorry, that's not what I meant to do, into 3 times 1 minus 2, what do I get? 1. And if you're not sure, you can test the next number. 3 times 2 minus 2 gives me 4, which is the second term in my sequence. Okay, so let me go back through how I created the 3n minus 2, because you are going to do this for me on your homework. Where did the 3 come from? That's the common difference. So we will always take that number that's the common difference and multiply it by n. And what that is in essence doing is getting that pattern that adds the 3 every time. That's why the 3 is happening there times the n. But we've got to get it aligned right so that it starts in the right place. So we just try the first number. We try putting in n equal to 1. If it works, we're done. If this sequence had been 3, 6, 9, 12, we would be done, and the sequence would have the pattern 3n. But it didn't start at 3, it started at 1. So we add or subtract a number to make it the right value as the first value in our sequence. When I had the number 3n here, had that value 3n, and I put in the number 1, I was getting 3. Well, 3 is exactly too large. It should be at 1. So I need to subtract the 2 that it is too large to be. Are we good? You'll practice and it'll be better, but that's how you think about it, okay? All right, let me move this up a little. All right, how about the next one? What's going on this one? It's multiplication by 2. Which makes it arithmetic or geometric? That will make it geometric. And can I find the next term? Sure can. What would come after 24? 48. And then 96. And then 192. And if you didn't do it in your head, you use a calculator, that's fine too. But again, if I wanted to find the 50th term, oh, I didn't say that on the problem before. Now if I have this 3 and minus 2 and I want to find the 50th term, it's really easy to do that, right? You just plug in 50 for n and you can find out that, oh, the 50th term is what? 148. Yeah, 50th term is 148. Okay, so if I were wanting to find the 50th term in this next sequence, first of all, we know it's going to be really large because this number is getting twice as big every time I do the process. Okay, so it's going to be a really big number. But again, I don't want to keep multiplying by 2 until I get to the 50th spot in the sequence. Excuse me. So there's got to be another way to deal with this that makes it easier. Okay? And just like on the last one, the common ratio was part of the sequencing formula. The common difference on the last one. The common ratio on this one will be part of it. Right? So my common ratio on this is what? 2. That's the multiply by 2 part I got. The common ratio is 2. So my common ratio 2 is where I start. Instead of taking 2 times n, because that would be adding 2 every time, I'm going to take 2 to the power of n. Almost. I'm actually going to need it to be the power of n minus 1. Because what this does is it allows me, if I put in the value 1 for the first term, what will that exponent be? 0. And what is 2 to the power of 0? 1. So that n minus 1 resets it back to be at the value 1 every time. So how do I get it to start at 3 then? Because this is not supposed to start at 1, it's supposed to start at 3. What do you think? Very close. We're going to actually multiply by 3.
Okay, wait. Will you just why it's n minus 1 again?
Yes. There are other ways to do it. Let me just say that first, where we could just let it be n. Okay? The beauty in letting it be n minus 1 is that when I plug in the number 1 for n, I get 0 as an exponent. And whenever I have 0 as an exponent, 2 to the power of 0 or whatever to the power of 0 gives me the number 1. So let me write what I just said down because you're still looking at me funny, Nicole. If I plug in n equal to 1, I get 2 to the 0 power. And 2 to the 0 power is 1, which allows me to multiply it by the first number. And I get 3 times the 1. It allows me to determine that times 3 much easier than if I'd had an exponent of just n. Because then I would have had to multiply and I would have had to add something both. I'd like to do as few things as possible. So if I make it n minus 1 as the exponent, all I have to worry about is what do I need to multiply by on the outside. And this is beautiful because the number I need to multiply by on the outside, it's just the first number in the sequence. That's all it'll be. All right, I've already answered this question before, so let's see if you were listening. Are we using inductive or deductive reasoning to do this? It is inductive, right? Go back to the front page. I have to go back to my first slide. Inductive reasoning is making generalizations. That's what this formula is we're creating. We're creating a general formula. We're making a generalization based on a pattern. So this is inductive reasoning. Okay? Okay, we're going to do one more that goes at this from the opposite perspective. On this one, we have formulas given to us. We're not creating them. They are given to us. And we are going to decide based on these formulas First of all, what are the first 5 terms in the sequence? And then, is it arithmetic, geometric, or neither? Okay. So when we're given a formula, it's pretty nice and easy to find the terms of the sequence because all I have to do is to do what? Plug in numbers into the formula. So I can say n equal to 1, and what happens when I put in this into my 5n plus 6? I get 11. So 5 times 1 plus 6, I get 11. I can do n equal to 2, and what do I get? 16. So I'm not going to write any more of them, but you're going to tell me. What comes after 16? What happens when n equal to 3? I get 21. What happens when n equal to 4? 26. Can you tell me what happens next without actually putting the number 5 in? I get 31, and then I get 36. How do you know? Because you're adding 5 every time. Now look back at that formula. 5n plus 6. Why are you adding 5 every time? Because it says 5 times n, right? Do you remember back over on this problem? The reason we used a 3 here is because I told you we're adding 3 every time. And notice over here, that 5 right there, that wasn't very good. Let's try again. That 5 right there tells us I'm going to be adding 5 every time. That 5 is my common, what? Difference. Is this sequence arithmetic or geometric? Arithmetic. Very good, guys. And just so that I'll write it down so that we have it. We said the common difference is 5. All right, let's try the next one. N squared minus 1. So if n equal to 1, what do I get on this one? Zero. How about n equal to 2? N equal to 4? 15. All right, so I have 0, 3, 15. Then what? I skipped n equal to 3. Nobody wanted to tell me that. Were you guys thinking that and just didn't think you wanted to tell me? Sorry. 15's there, it's just too early. Okay, what was 3 squared minus 1? 8, right? Remember, 3 squared would be 3 times 3, not 3 times 2. Yeah, so it's 9 and then minus 1, so this is 8, and then I had the 15. What comes after 15? It's the last one. 24. All right. Is this arithmetic, geometric, or neither? How do you decide if it's geometric? Okay, the n does have an exponent, but let me talk about the pattern itself that you just created. Let's look at the pattern. The pattern was 0, 3, 8, 15, 24. What will have to be true about the pattern for it to be geometric?
It has to go up.
Okay, what do you mean by go up by?
The numbers have to change by the same.
Okay, changing by the same amount is for arithmetic.
Multiply by the same.
They have to multiply by the same amount to be geometric. All right, so good. That's what I'm going to, they do have to go up by. We just want to be careful how we're using the word go up. Do we mean adding or do we mean multiplying? So if we're looking for addition, then we're looking for arithmetic. And is this one arithmetic? No, it does not have an addition fact that it goes up by every time. Is it geometric? Does it multiply by something to go up the same amount each time? No, and the very fact that there's a 0 in the sequence just has a problem already, right? Because I can't multiply 0 by anything and get any higher. So this one's actually neither. Now let's go back to what you noticed about the powers. This says n squared minus 1. Over here I had a pattern that said 3 times 2 to the n minus 1. I know the number 3, the numbers themselves are a little bit different, but what's really different about these two formulas?
The n minus 1 is supposed to be the power.
Yeah, it's where the n is. The n is in the exponent if it's geometric, right? This has n minus 1. The n is in the exponent, and here the n is not in the exponent. It's the base. Do you guys see that? So you're right in noticing that I've got the exponent. It's just that the wrong thing's in the exponent for it to actually end up being geometric. The other thing, too, is that notice for the geometric, the way that we're working with it, we don't have anything added or subtracted at the end. Now, that's possible, and you could have something that was set up that way, but and like this problem has that feature, but we're not creating ours to do that on purpose. Is it inductive or deductive reasoning? It's deductive, but I get the feeling that you're telling me it's deductive simply because we didn't give that answer before. which is true, we didn't. But let's talk about why it's deductive. See, I know you so well, and we've only been together for 3 days. All right, let's look at what this says. Deductive reasoning uses mathematical axioms, theorems, or definition, undefined terms assumed to be true for logic or proof. Deductive reasoning takes a formula, something you know to be true, and makes predictions based on that. In this over here that we just looked at, we are given a formula, 5n plus 6. We're given a formula, n squared minus 1. And we make our predictions based on the formula. Whereas over here, we were given previous data, and we're speculating based on previous data what's going to happen next. Can you feel the difference? We actually know for sure something to be true, and we're making decisions, or we're guessing it's true based on our previous experience to make those decisions. That's the difference. So this one is deductive reasoning. All right. Okay, we'll do one more, simply because it pulls in the last definition that we haven't explored too much yet. This says we're going to find a counterexample for the following. So without looking, everybody look at me. What does counterexample mean? Something that proves it false. Very good. So a counterexample is an example, but it's an example that shows that it doesn't work. All right? Now I want you to take a look right here. It says if n is a natural number, then n plus 5 over 5 equals n plus 1. First of all, before we find a counterexample, I want you to look at and tell me. So tell me, looking at that n plus 5 over 5, if a student did this and their answer was then n plus 1, what did they do to get n plus 1? They what? Divided what? All right, so they divided the 5 by the 5, or they might have used the phrase something like they canceled the 5s. People like the word cancel, which is just a horrible word because we cancel things and they become 0, and sometimes we cancel things and they become 1. Cancel's a bad word. So not like a real bad word, but it's just not a good word. All right, so this is probably what they were doing or thinking is something like this, right? They divided the 5 by the 5 and they got the 1. Okay, what else could they have done? Well, they also might have done that and said they got a 0, again, because this bad notation about this idea of canceling. So they might also have said, oh, this cancels out and it becomes 0, and they give the result as this is just equal to n. So we're going to actually show it's false. So a student does this on your paper and you tell them, no, you can't cancel those 5s. You can't divide out those 5s. And you'd like to show them why. And one way to show somebody why something doesn't work is by giving them a numerical example, plugging in numbers that show it doesn't work. Now, the beauty is that most of the time when something doesn't work, it doesn't work for most numbers. So there are most numbers you could plug, most numbers you can plug into this, it's going to fail. If you pick a number that works, just try something else, and you're probably going to get one that's going to fail. Okay? So pick something. What would you like to let n be for us to try? 3. I hear 3s and 4s. Some of you do 3, some of you do 4. I've got 3. All right, so let's see. What in the world would 3 plus 5 be? This would be 8 over 5. So if we simplify with the actual numbers in there, we get this. Now, if we do what the student speculates to be true, that is that this turns into the number n, which was 3, plus the number 1. So basically I'm plugging in the number on the other side of the equation, what they are thinking is going to be true. What is 3 plus 1? It's 4. Does 8 over 5 equal 4? No, it does not. So I put the same number in both sides of the equation, and I showed that the two sides of the equation don't actually end up with the same result. Right? What number could you put in here that would make it work? Do you see it? Nope, 5 won't work. 0. If I put the number 0 in, this will work. So you do have to be a little bit careful. For the most part, as long as you avoid things with zeros and ones in it when you're doing examples, you can usually avoid the pitfalls or the problematic spots, places where things actually are true when they sort of shouldn't be true in general. All right, so this is a counterexample. So let's say that you're talking to a student now about why in the world this is really happening for real. Like, this is the counterexample. I'm done with the question. But I want to show you what's really happening in terms of the mathematics behind what you're seeing. That is, if you had an exceptionally bright student who was working on this problem and they saw the counterexample, but they still wanted to know the why, not just an example showing it didn't work, here's the why. This is using addition backwards of fractions. Normally we start on the right-hand side of this and we move to the left. You know, you get a common denominator and you add the tops. But you can separate them back out just as well. This is actually equal to the n over 5 plus the 1. What the student did is the student forgot to divide both parts by 5, right? They only divided one of the numbers by 5. Now, this is actually true. And any number you put in to n plus 5 over 5, and you put in to n over 5 plus 1 will work. Any number will. Any questions on that? That part at the end, that's just for free. That was bonus information today, not in my notes at all, okay? Just for fun. All right.